Everyone. Thank you so much for joining us today for our webinar, Stopping Financial Crime in Real Time, How Graph Analytics Unmask Hidden Fraud Networks. I think we'll get started right now. My name is Victor Lee. I'm head of product marketing at TigerGraph, and I'm really excited to be presenting this very valuable and thought-provoking information for you today. And the problem that we're talking about is financial crime and how it's such a major issue today. If you think about it, digital payments are now dominate consumer activity in the US and around most of the world. Um, Personally, I hardly ever carry cash with me. I pay for almost everything either with a credit card, as 35% of transactions in the US now are, or with a debit card, another 30%, or a direct bank-to-bank transfer, which is another 13%. So 78% of consumer payments are digital, which means they happen in like a fraction of a second, maybe sometimes a little bit slower, but on the order of a second, with a total of over 100,000 payments every minute of every day. So it's a massive scale. Among that, there's always some fraud, right? And there's so little time to catch it. You have only, maybe at most 100 milliseconds for a financial institution, for a retailer to try to evaluate whether this is a valid transaction or a fraudulent one. The problem is huge. It's right now 34 billion. In a few years, it's going to be up to 40 billion. And that's because it's growing. It's growing every year. Within the US, it's growing about 10% a year. In other countries, it's growing up to 25% a year. And how much of that, of how much dollar-wise? While only, maybe a couple percent of transactions, maybe less than 1% of transactions, but the dollar amount is higher than that. That's because there are added costs. There's more than just the direct cost of the transaction. There are administrative costs, there are investigation costs, opportunity costs, and also some of those transactions, they may be averaging, their size may average larger than the average transaction. So it's a massive problem, and there's obviously a lot of desire for both financial institutions and retailers and consumers to overcome this problem. So there's been work, obviously. Conventional fraud detection is doing the best it can, but it's not doing enough. And that's because fraudsters know basically what the financial institutions are trying to do, and so they work around that. It used to be a very manual process. Now there's more AI involved, more automation on the fraudster part. And so the technology on the detection side has to keep up. So not only are fraudsters getting away, but innocent consumers who are just doing completely legitimate business, if the detection system isn't accurate enough, then they may be falsely tagged and accused of being fraudsters. Last time I traveled overseas, my first transaction was blocked. I'm kind of glad that my credit card company, was careful, but it would have been nice, they had no way of knowing. But that's the sort of issue that's going to happen. So, very simple rule. Well, if the amount's just larger than usual, block it. But, people's legitimate needs vary in size. As I said, I traveled out of the country, and so it blocked my transaction. But hey, it was really me. And there are other things they look at the exact address of where you say is your home address, what electronic device you're using. Your cell phone, is this actually somebody else's phone? What IP address is the IP address, in some strange location? The time of day, is it really, really early in the morning? It would be unusual for you to be eating in a restaurant because the restaurant isn't open. So these are the types of things that they look for, but again, they're imperfect. What they need to do, what the financials need to do, is study the data more deeply, because there is a certain number of fraudsters behind this. And if you can follow the connections to see who is orchestrating this, who actually, they may have some partial information that is true. And if you can piece together the partial information, you can see that, oh, these are known fraudsters. This party, if you follow the links, you can see the connection. Or sometimes a set of multiple transactions and multiple relationships adds up to a certain pattern. In money laundering, there's a certain pattern of structured layering of where they spread out money and then reintegrate it. But in other types of fraud, there's similar patterns. And if you can look at the larger picture, you can do a better job of detection. But you have to do it fast. As I said, it has to be done in like 100 milliseconds. And with, again, 100,000 transactions, not at one institution, spread across the industry, but there are a few large banks that do handle the bulk of the business. And so Tigergraph has been able to help out those companies. We're saving them and we're saving you money by increasing their fraud detection by approximately 20%, increasing the efficiency of their investigative teams when for things like money laundering or other types of fraud that aren't just the split second decisions but require some analysis afterwards, netting a savings across our customers over $100 million a year. And that's on very large data sets because I said that while there are banks of all different sizes, the largest ones are handling, tens of millions, 100 million accounts with billions of dollars in transactions. That's obviously a lot of data to be handling. And we do that in real time with, in one case, I'll talk about the analytics is in under 80 milliseconds. Here is that case, JP Morgan Chase, the largest credit card issuer in the US. They reported saving $50 million through Tigergraph's added fraud detection capabilities. The problem, as I mentioned, they were doing the best that the industry could do with conventional means, but they were still missing some of these more complex patterns. The fraudsters are spreading out their activity, creating synthetic identities, stolen credit card information, or again, synthetic identities, and costing hundreds of millions of dollars. The problem was they sort of knew in principle that they needed to look deeper, but it couldn't be done in the amount of time that it had to be done. In order to keep customer satisfaction, they have to process those transactions very, very quickly. So they turned to us and they realized that graph analytics would be the answer because graph lets you see those connections. And if you have a native scalable graph like Tigergraph, you can analyze those connections very, very fast. And so by using Tigergraph, they integrated some of those analytics into their existing machine learning algorithms to give them additional graph features which were more insightful, giving them a deeper look into what's happening, adding that to their machine learning training. And the results were, again, improved detection, not only catching more real fraud, but also reducing the number of so-called false positives when a legitimate transaction, a legitimate party gets incorrectly classified as fraud. So for that $50 million a year, that's a ballpark figure. The exact numbers are proprietary, but that's the ballpark. And they're serving tens of millions of households, like 60 million. They have even more accounts than that. And the size of their data, again, is massive. Tens of terabytes of data as in their collective graph. And so there's both a training process, training the data for the model, and the deployment of in real time scanning the relevant data to make a real-time prediction. So that's sort of what you consider like a mainstream case, but there's another type of bank out there, which is called sometimes called neobanks, and that's because they're digital first. These are newer institutions that are not built around um, brick and mortar off branches that you visit, but really all the activity is online. Um, and so Nubank is Latin America's largest such neobank with, again, millions of customers. There are extra challenges when you're doing all that digital activity and trying to move quickly and trying to move fast and innovate, that they were seeing a significant number of scams. Again, and in particular, something called mule accounts, where there is a fictitious entity created which sets up an account, and the account is used just to funnel money. And it's often part of a larger money laundering scheme. So, using their, again, legacy system, they had 60% false positives. That means for every prediction of fraud they made, 60% of them were actually legitimate people. And they were only catching 28% of the actual fraud. So they were missing quite a bit. And this was over 65 million accounts. So another huge problem. Again, using Tiger Graph and our native graph, the analytics, the intelligence that you get integrating into the machine learning pipeline. In this case, 30 graph features used in real-time analytics to find things such as proximity to known meal accounts, community detection to group accounts together. Again, delivered the real-time insights that helped improve their capability, again, saving millions of dollars per year, 65 million households. So spread across Latin America, a similar amount of households as in for Chase in North America. And in their case, using 30 graph features, which again are all run in real time to give them added intelligence into what is the network of activity, what is the relationships going on to trace to see who are the fraudsters. Now, I want to give you a little bit deeper look into how this works and start off by looking at traditional machine learning. Traditional machine learning, you have your source of data. Some of it is your stored data about the biographical information about your account holders and merchants. Some of it is the real-time transaction data. You design a system which takes features from that data. So you have what you call entities like an account holder, a party, a merchant, those are entities. But then they have characteristics, their location, the size of the transaction, the time of day. Each of those facts we call a feature. So you gather those features, and you also have some known fraudulent activity from past historical information, and you prepare that data into a nice table or matrix and submit it to one of several conventional machine learning methods, and it studies the pattern. It basically looks at when does fraud occur, what were the features when fraud did occur, what were the features when fraud did not occur, and how do I distinguish between them? Can I find a certain characteristic collection of feature values that is good predictor of fraud? So that's basically what machine learning, supervised machine learning is doing. And it's going to give you a certain level of performance. And the performance is going to be based on the quality of the data features you were able to provide. If you were able to provide really meaningful features, then you can get a good prediction. But if you have a small or not very informative set of features, then the prediction isn't going to be very good. So there's actually a lot of work. It's not just it's just not the neural network or the decision tree. It's the quality of what can you tell it about the circumstances. This is what the data features is doing. When you use graph, you are giving an incredible boost to this phase. So first, you gather some of the data and you recognize, you acknowledge that things are related to one another. Um, people, there are multiple persons who are using the same account legitimately. There are people who live within the same zip code. Again, all you gather this connected information of households who have people transacted with in the past, um, and such like that. You then do feature engineering on that connected data, and we'll talk about some of the more specifics there. But this is the secret sauce. It's that when you look, this is revealing the patterns. This is showing you how that new unknown party or transaction is actually only a few hops away from numerous fraudsters. And again, while that by itself is not going to make the decision, it's the collection of the multiple features in concert and looking at the pattern and being able to make stronger statistical predictions. Maybe as we saw with Nubank, only 28% recall. There's obviously a lot of room for improvement, and this is where they're getting that improvement. You then train a machine learning model using much the same technique. Again, the real added benefit was the added insight from the data features. Once you have this is the case of quality in, quality out. I don't want to I don't want to use the old phrase of garbage in, garbage out, but this is the case where if you can give better quality data features in, you're going to get better predictions. So it's the same type of model. It's the better training data that leads to better results, resulting in higher percentage of fraud detected, lower percentage of false positives, and you get explainable results because you can look at the graph and see the connections. So now I'm going to walk you through really this solution kit that TigerGraph offers to help other financial institutions quickly bring up this capability. We've worked with so many customers to solve this type of problem that we've been able to build reference examples with schema, with data, with queries, and with analytics dashboards to show you exactly what to do. Excuse me. So I'm going to walk through the solution kit for transaction fraud. You can see we also have kits for 3 different types of financial crime, for entity resolution recommendation, and for digital twins. But today we're going to focus on transaction fraud. So, excuse me, within TigerGraph Cloud, Savannah, our cloud offering, you can, from the marketplace, select one of the 9 solution kits. You can actually deploy it at the same time that you're deploying a new workspace, or you can add it to an existing workspace. And then within just a few minutes, you will have the kit installed on your workspace. So again, the kit includes a graph schema, sample data, queries and other analytics. Um, if you need some scripts to run the whole process, they're there. And it can use Insights, our dashboarding tool, to highlight what is the aggregate activity that's happening so you can evaluate the degree of success you're having. This is a look at the dashboard for the transaction fraud kit. You can see it's got a first column is talking about the characteristics of the data. This is the sample data, but you could ingest your own data. Then if you've run the analytics, you can then evaluate the performance, and it's doing an A/B comparison between with graph features and without graph features. And given some assumptions, it shows the economic benefit of what you're doing. So zooming in just on the data set characteristics, this sample has about 860,000 transactions. That's it's big enough to show the compute power of what's happening, but it's obviously not as large as what our customers are using. The thing is, this is very convenient to run even on one of Tigergraph's sort of value priced deployments, certainly Tigergraph has the scale, it could go far larger, but you can run this very easily on a smaller deployment on Savannah or on-prem on your laptop. And see, fraud is only like one small fraction, and that's what makes it so hard to predict. That most of the time, 99+% of the time, transactions are not fraudulent. So it's finding a needle in a haystack. And the data is representative of sort of consumer shopping. We also give you a graph schema. This does look pretty complicated. You don't need to memorize this in any way, but I'll just talk you through a few key points. We're modeling the credit cards or debit cards. The transaction itself is considered an entity. Transactions are associated with a merchant and a card, and the card is being used by some party. As I said, um, a card might be shared by multiple persons. That's why there are multiple parties. That's why it's considered separate. These nodes are characteristics of the party, such as, the date of birth and the ID number, what device they happen to be using for this transaction. Over here, we have community. This is not part of the source data. It's something that we're going to generate in the analytics, which I'll point out later. And recently, we've added this node concept, and this is used for AI integration. If you have some, say, text data to talk about some of these things, you can use an LLM service to do entity extraction from the data and create a knowledge graph with LLM embeddings and do AI investigative querying of the data. We're not going to have time to go over that today, but that's an exciting addition that we'll be talking about in the future. With the kit, you also get over 50 custom queries. Some of these are just for data preparation, but most of them are those data features. As I said, it's the data features that are really adding the value. They are a summary of, they're sort of a numerical assessment of a characteristic, and I'll show you some examples. You also get a Python notebook because, as I said, this is for machine learning. TigerGraph is a high performance graph database and graph analytics platform. But to do the overall task, the financial institution needs to train a machine learning model. So TigerGraph has integration. We have a Python driver. We have a library of algorithms and other machine learning related tools so that you can work together with a conventional machine learning system. It's not proprietary. There are industry standard open source ways of working with machine learning, and TigerGraph integrates very conveniently and smoothly with those. So what we have is a Python notebook that walks through the steps of how you would run build your machine learning system, build your machine learning model. Just a reminder of this diagram. When you deployed the solution kit, it already loaded the data into the graph. If you have your own data, we have example loading jobs to show you how to do that. We're now going to talk about the graph feature generation. Then we'll show that we go through traditional machine learning model training. So, first features that we generate, we form communities. We have two communities in particular, those around the credit cards and those around the merchants. This is a screenshot of just the introduction to the G-SQL code for one of these two queries. And the intuition of why you want to do this is that if a merchant or card is within a community with suspicious activity that already has some suspicious activity, just by association, it's more likely to itself to be a fraudster. And so what it's doing is it's looking for groupings where there's a relatively high number of connections within the group and relatively few connections going to other groups. So it's looking at the density of connections, the pattern of connections, and it's coming up with these boundaries. So that is what community detection is, and that's what these algorithms are doing. They are deciding where is the best line to draw these communities and then group them and make decisions based on, hey, are you in the same community with known fraudsters or not? The second phase is to run through these other graph features, and you can see this is not all of them. There, as I said, there are 50 of these, so this is just a subset. But you look at the community size. All of these turn out to be a numerical score because machine learning systems like to work with numbers. PageRank, if you're familiar with the PageRank algorithm used for understanding the importance of different web pages, here we're looking at the amount of money flowing in, not just directly, but sort of multi-hop level. PageRank looks at actually recursively all the levels throughout. When you look at the whole holistic pattern, not just direct neighbors. Is there a lot of money or is there a lot of activity flowing into this node or not? The larger nodes represents the ones with larger share of activity. Those are the ones with higher scores. Shortest path. How close are you to a known fraudster? And or how many are there within the same community? What's the distance? These are all useful scores. And you can see what's the average amount of a transaction within a community, how many such transactions, etc. And I said there are something like 50 of these. And the thing about machine learning is when you're first developing a model, you don't know which of these are the most important features. That's why you're using the ML. The ML is supposed to analyze the data and tell you which features matter. So, don't put the cart before the hearse. Don't try to predict, oh, this is the feature I should have. You come up with a lot of possibly interesting features and then have the machine learning tell you which ones were actually valuable. Um, Now that we have the features, we combine the graph features and the other features that you already had, even without the graph. And we partition the data into training and test sets. And then we do two sets of training because we're doing a comparison here. We're doing an A/B test. How well do you do with graph? How well do you do without graph? And here are the results. Again, looking at our dashboard, so let's start at the bottom. We're trying to see how well are we predicting. True positive is when you are detecting real fraud. And you can see with TigerGraph, there's about um, a 5% increase. And false positive, this is when you are, falsely accusing somebody of being a fraudster when they really aren't, or a transaction. And that goes down. So both of these moved in the right direction. The statistic called recall went up by 2.6%. The precision went up by 17.2%. So now this is just synthetic data. This was not real world data, but it is in a synthetic data that we got from a public source. So you could duplicate this results. And of course, the banks we work with, they have their own real world data, and they're telling us that they're getting on the order of 20% improvement. So these are very representative numbers. Those statistics are great. What is the economic impact? A simple way of looking at it is every time you block a fraud transaction, the value of that transaction is money that you saved. Now, it's not quite in the real world, it might not be so black and white. As I said, there's actually overhead. It's actually each dollar of fraud actually costs a bank like $3. So it's actually higher than this. But also, when you do not block a legitimate case, but previously you were, that also is money saved. Because now you've allowed that business where previously you were not allowing that business. And that's how they make money. They make a little percentage on each transaction. So even for our larger financial institutions, just 1% of improvement means millions of dollars in savings every year. So if you're saving 20%, That's again tens of millions of dollars of savings. So this is these machine learning can be a game of incremental improvement. As I said, 1% improvement is worth millions of dollars for a larger institution. So I hope that didn't bore you too much. I find it interesting. Obviously, I've got both a technical and sort of a customer focused background. The bottom line is fraud is hurting, not just businesses but consumers, and there's just a lot of desire to catch it. And to do that, you have to look deeper at the data, and a scalable high performance graph like Tiger Graph has been proven to be the most effective approach for doing that, with saving 20%, I mean, increasing the accuracy by 20%, making the investigative analytics 300% more efficient. So when a person has to sit down and look at the data, resulting in millions of dollars in savings. Um, can you do this with any graph? Well, you're gonna see that in principle, graph is what you need, but you and why? Because you want to represent the related data, relationship data, but you need a platform where you can traverse that data very quickly and efficiently, and you need those, either the query language or the algorithms, to generate those features. So it's not just any graph, but you need an analytical graph and one that scales and fast. And that's why Tiger Graph has been the choice for these large financial institutions as well as medium-sized institutions. It's because of that compute and analytical and scalable performance. So thank you so much for your time. Again, my name's Victor Lee.